Okay, so let's look at those two examples that we still have here. The example says the following. The given circuit shows a parallel combination of an inductance and a resistance. If it's desired to connect a capacitor in series with the parallel combination such that the net impedance is resistive at 10 megahertz, what is the required value of C? So the first thing we need to do is to first go to the frequency domain here, where those inductor and capacitors are as a function of the frequency. So in this case, I will redraw the circuit. Now, here we have ZC, we have R, 300 ohm, and we have ZL that we need to find. So the first one is ZL, which is J omega L. In this case, the frequency has been given to me. Here we have F. So F is 10 megahertz, right? So omega here is J 2 pi F L, or ZL as J 2 pi times 10, L is 20 micro Henry. So ZL as J 120 times 20 is J 400 ohm. So this is the impedance for the inductor, J 400 ohm. The impedance for the capacitor, ZC, is 1 over J omega C, or ZC is, when J goes up, becomes minus J over omega is 2 pi times 10 to the power 6 times C. Now C is unknown, so ZC is so we have here 20, so 10 to the power minus 6 minus J over 20 pi C. Okay. Now we need to find the total impedance here. So the total impedance, if you look at you have here the 300 and the J400 are in parallel. So in this case, we will find, let me call this one as Z1. So I have here Z1 is 300 times J400 over 300 plus J400. I need to find the equivalent here. So Z1 is 10 to the power 4 J. And J is, I can replace J here with 90 degrees, right? I will convert the denominator to the polar. So in this case, the magnitude is square root of 300 plus 400 with tan inverse of 400 divided by 300. So in this case, Z1 is 12 over 4, 90 degrees divided by 500 with an angle of tan inverse 4 over 3 is 53. This is first quadrant, 0.13 degrees. Then Z1 is 240 with an angle of 90 minus 53.13 as 36.87 degrees. So this is Z1, which is now the equivalent impedance for the resistor and the inductor that are in parallel. So this is Z1 and this is ZC. Now, what is the total impedance here? Zn is ZC plus Z1. Now, when you're adding those two impedances, wouldn't it be 400 pi ohms? Where's the 400 pi ohms? I missed the pi, you're right, yeah. J400 pi. Yeah. J400 pi ohm. J400 pi. We have the pi here. We have the pi. Yeah. Okay. So now the total impedance Zn, after we found the equivalent impedance for the inductor and for the resistor that are in parallel, 22,400 pi. Okay, now we have it here. Okay. So the total impedance now would be Zn equals to Zc, which is minus j 10 to the power, okay, sorry, minus j 10 to the power minus 6 over 20 pi c plus this 240 pi. We can convert it back to the rectangular format in order to 240 pi cosine 36.87 degrees plus j sine 36.87 degrees. Okay, to convert it to the rectangular format. So we have here Zn as minus j 10 to the power minus 6 over 20 pi c plus 240 pi cosine 36 is 0.8 plus j 0.6. So in this case, we have Zn minus j 20 pi c 240. Let's leave the pi. 240 times 0.8 as 192 pi plus j 240 times 0.6, 144 pi. So now the question is asking, what is the value of the capacitor if the input impedance is pure resistive? What does this mean? This means that the reactive part would be 0. So if we come here, if we say that this Zn is made of resistive plus Jx, where x is the reactive. So in this case, this one would be the resistive part, and those would be the reactive part. So let me take now this reactive part, which is, let me say here, x equals to j, or let me say jx equals to 144 pi minus j 10 to the power minus 6 over 20 pi c. Jx equals to, let me take the J outside, J 144 pi minus 10 to the power minus 6 over 20 pi c. So in order for the impedance to be pure resistive, this x has to be 0, which means x should be 0. And in this case, I have 144 pi minus 10 to the power minus 6 over 20 pi c is 0. Or 10 to the power minus 6 divided by 20 pi c is 144 pi, right? Or 20 pi c over 10 to the power minus 6 is 1 over pi, or c equals 10 to the power minus 6 divided by 144 pi squared times 20. So C is 0.35 to 10 to the power minus 10 farad. Or C is 35, almost 35 picofarad, where pico is 10 to the power minus 12. Okay. Any question about this problem? Any question? No questions? Okay, so basically this is how we found the value of the capacitance when the total impedance is resistive. Now let's move to our last example here. In this example, we will be using or applying the nodal analysis in AC steady states in order to find the current Ix. Okay, so we've seen how to find the Thevenin's equivalent circuit in AC steady states. Now we will be using nodal analysis, and you can also use mesh analysis. Sorry about that. And AC steady state. So I would like you here to participate in solving this example, just to try the AC steady state, the nodal analysis in AC steady state. So what is the first thing we should be doing here? If somebody can tell me, this is, now you got this question, the exam, for example, find the nodes. Okay, I'll find the nodes. So I can circle the nodes as you said, or I can use the coloring. But since here I have the ability to do the coloring easily, I'll use the coloring here just to make it. So I have the nodes that I would be writing the nodal equations for, right? So I have here this node. Okay, and the orange here, this node. Okay, so I have 1, 2, 3, 4 nodes. But before I do any further assignment to the voltage to those nodes, the first thing I should be doing is, this is a time domain, and this is an AC steady state. How did I know that's an AC steady state? Look at the source. The source is a sinusoidal function, right? The source is a sinusoidal function. So before I do anything of what I have learned in nodal analysis, I should do something important here. Can somebody tell me, what shall I do? Yes, that's correct. So I will redraw the circuit, and now I won't be having Henrys or farads or sinusoidal functions. I will be only having impedances and phasor representation for that source. So I will redraw the circuit. I have a capacitor here. I have an inductor. Another inductor here. Resistor and a source. So always remember that our reference function is the cosine function. So here we have, this is 10 ohm. Nothing is going to change for the resistors. Now this one is 2 Ix. We use capital, right? And phasor. So this current now is Ix capital. And now this source becomes 20 with a phase angle of 0, right? Now the inductors, now here I have 2 inductors and 1 capacitor. So let me call this one Z1.
All right.
Yes?
Why do we convert to the frequency domain?
Because this is the way we have learned to do the analysis in AC steady states. how are you going to treat those inductors and those capacitors? You have a circuit that basically is working as an AC steady state, and those capacitors and those inductors are a function of those frequencies. So how are you going to represent them?
So because it's AC, it's how you would represent Henrys and farads as compared with our voltage source.
Yeah, here we're not dealing with a transient response. Here we are dealing with a steady state signal. That's a steady state signal. However, it has a frequency. It is repeating itself. It's not a transient. You go from DC state to a DC state. Here you are within an AC steady state. So we use the impedances. So Z1 here for me is J omega L1. Do I know the omega? Do I know the omega? Do I know the frequency for my circuit? Yes, that's correct. The frequency is 4 radians per second. So here I know omega, this is omega, is 4 radians per second, right? So Z1 is J4 times L. L is 1 Henry. So Z1 here is J4, and the unit is ohm. What about Z2? So here J4 ohm. This is Z2. Z2 is J4.5. Z2 is J2 ohm. Notice that the impedances for the inductors are always positive. J2, J4. Look what is going to happen with the Z3, which is the impedance for the capacitor here. Z3 equals to 1 over J omega C. And this is minus J over omega C, right? So Z3 is minus J over 4 times 0.1. So Z3 is minus J of 2.5, right? So those are the first steps that you should be doing. If you have a circuit in AC steady state and time domain, you have to go to the frequency domain. And notice that the impedance for the capacitor is negative, minus J 2.1 ohm. Okay. Okay, now I will define my nodes, what I did earlier. This is a node. It's a node. It's a node. That's it. Now, which nodes I need to write the nodal equations for, and which nodes I don't need to write the nodal equations for, because they're not gonna help me in my analysis. Which ones that I should be considering to write the nodal equations at? Number one, when you do nodal analysis, your variables, your standard variables are, what are your standard variables in nodal analysis? That's correct. I need to write for the red and the green. Which variables would be assigned to those nodes? What type of variables? Voltages. So this is extremely important. Nodal analysis, we're solving for the voltages at those nodes. And as your colleague said, we will be considering only the red and the green. Why not the blue? Can somebody tell me why we don't need to write the nodal equation for the blue node? The voltage is known. That's correct. So the voltage here is known because I have the reference here. My reference is here. For this voltage source, the voltage at this node is known, and it's 20 volts. But I don't know the voltage here, V1. I don't know the voltage here, V2, okay? So that's what I need to know. This is my reference, 0 volt. That's my reference. So let's write those equations. Let's start with the first node. Nodal equation at V1. And notice that I have taken V1 and V2 to be capital, because this is what we have decided at the beginning, that when we go to the phasor, to distinguish between the phasor, the polar format, and the time domain, the time domain is small letter, and the phasor representation here would be capital. So V1, can somebody tell me what is the nodal equation at the node that has the voltage V1? I need a volunteer to give me the nodal equation at V1. I'm sorry, this is, hold on a second, this is minus J2.5, and this is positive J2, this is J2. Minus J2.5. J2. Okay. So V1 minus 20 over 10 plus V1 over minus J 2.5 plus V1 minus V2 over J4. Excellent. So keep in mind that V1 here is connecting, as you can see, three components. The 10 ohm, the minus J 2.5, the J4, right? So when you write another equation, you're expecting to get the same fractions here as well. So you have V1 minus 20, and I will remove the 0 because the 0 here, the phase angle of 0 basically means 20 because cosine 0 plus J sine 0, right? So this is V1 minus 20 over 10 plus V1 over minus J 2.5 plus V1 minus V2 over J4 equals 0. Thank you. Now, the second equation, nodal equation at V2. Who's willing to give me the second equation? You don't need to write it. You can use your mic and you can say the equation. Volunteer, second volunteer. Okay, go ahead.
Okay, so would it be V2 minus V1 over J4 plus V2 over J times 2? I think that's it. Oh, wait. And then plus V2 over 2 times IX.
Hold on a second. That's very important. Why did you say V2 over 2IX?
2IX. Oh, shoot, times 2.
Okay, hold on.
I was thinking of it in the same vein as a resistor, but...
Okay, so let's think of it this way. What is V divided impedance? What is voltage divided in? This is V2 minus V1 over J4. So this is voltage divided by impedance. What's this? That's current. Right?
Right.
But you have the current ready. It is 2IX. Right?
All right, so just equals 2IX.
Minus 2IX.
Minus 2IX.
It is entering the node, right?
Right.
So minus, I will write it even in different color. Equals 0. That's it. V2 over J2 plus V2 minus V1 over J4 minus 2IX equals 0. Now, if you want to verify the number of the components that are connected to this V2, you can count them. 1, 2, 3. And this is what you have. 1, 2, 3. Indeed, those are currents. Those are currents, but we have learned how to write it by inspection right away looking at the circuit. But if you recall, how did we derive the nodal equation? We derived it from the currents in those branches. We added the currents such that they're leaving the node, right? We assumed they were at the beginning that they were leaving the node, and that's why we wrote the equation as we added those currents. But now here we have 2ix entering the node, and that's why we wrote it as minus 2ix. Okay, so we're done with the nodal equations. However, because we have a dependent source, this dependent source has introduced for us an extra variable, that is ix. So what shall we do? Can somebody tell me now? So looking at this and those equations, I can see that I have v1, my first variable. I have v2, my second variable. And now this dependent source introduced to me a third variable, ix. What shall I do? Okay, so basically what you should do in this case, yes, you're right, ix is v1 divided by minus j 2.5. But why did you come up with this expression? Well, because we have seen earlier that whenever we have an extra variable that comes from dependent source, we need to look in the circuit, how can we write this extra variable in terms of my standard variables, which are v1 and v2. Those are my standard variables that I would like to solve, v1 and v2. So I will look into the circuit, and I can notice that the circuit is giving me this, saying that this ix, by the way, that the dependent source is depending on, is indeed the current that is going in the capacitor. Okay, so what is the relationship of this current going in the capacitor with my standard variables? Well, v1 here, and the ground is here, so the current is going in this way according to the passive convention that we talked about. I can say that indeed this ix as v1 minus 0, which is this, divided by minus j 2.5, or ix is v1 divided by minus j 2.5. So this is the expression that I have derived from my circuit, knowing my standard variables, right? What I can do now is I can take this ix and substitute it in this equation, and then I will be getting the two nodal equations, two equations, two unknowns, and then the problem is solved, right? So if I go here and I rewrite those nodal equations, so from this one is v1 minus 20 over 10 minus v1 over j 2.5.
Sure.
Yes.
Would you actually recommend algebraic substitution using complex numbers?
I'll let you pick the way you want to solve it.
Right.
Solve it the way you want. minus 2 ix becomes v1 over j 2.5 equals 0. Right? Minus 2 v1 over 2.5. So those are my two equations that I need to solve simultaneously. Okay. So here, if I multiply this by 10, I have v1 minus 20. When j goes up, this becomes positive j, right? And I have j4 v1 minus j 2.5 v1 minus v2 equals to 0. Okay. So if this is 1, then we can say v1 minus 20 plus j4 v1 minus j 2.5 v1 plus j 2.5 v2 equals to 0. Then this is v1. This is imaginary v1. Imaginary. So we have v1 j4 minus j 2.5 as plus j 1.5 v1 plus j 0.5 v2 equals 20. Or v1 1 plus j 1.5 plus j 2.5 v2 equals 20. So this is the first equation. The second equation, if you multiply by 10, you have minus j 2.5 v2 minus v1 minus j 5 v2 minus j. So this is going to be 4 times 2 minus j8 v1 equals to 0. right? Let's have a second look here. So the j goes up, becomes minus j 2.5 minus j 2.5 v2 minus v1. J goes up, becomes minus j 10 times divided by 2 is 5 minus j5 v2. And then this j goes up, becomes minus j. Then I have 10 divided by 2.5, which is 4. 4 times 2, which is 8 minus j8 v1. Or minus j2.5 v2 plus j2.5 v1 minus j5 v2 minus j8 v1 equals to 0. So we have here both are imaginary, right? So we can divide by j. So this becomes minus 2.5 v2 plus 2.5 v1 minus 5 v2 minus 8 v1 equals to 0. So we have minus 5.5 v1 minus 7.5 v2 equals to 0. Then v1 is minus 7.5 divided by 5.5 v2. Now take this one and substitute it in one of those two equations that we found. If I am to call this one then 3 and 2 minus 7.5 can keep it equals 20. Right? Then you can find v2. Do you have one? Okay, so here minus if I multiply by 5.5 multiply by 5.5 minus 7.5 1 plus j 1.5 v2 plus j 13.75 v2 equals to 20 times 5.5 and 110. So minus 7.5 v2 minus j 7.5 times 1.5 is 11.25 v2 plus j 13.75 v2 plus 2 10. Now 13.75 minus 11.25 is 2.5, so we have here minus 7.5 v2 plus j 2.5 v2 equals to 110. So we have here minus 7.5 plus j 2.5 v2 equals to 110, and v2 as 110 divided by minus 7.5 plus j 2.5. v2 equals to 110 divided by minus 7.5 plus 2.5 tan inverse of 2.5 divided by minus 7.5. Be careful to the phase angle, which quadrant. So we have here square root of 7.91 tan inverse of 2.5 divided by minus 7.5. When you use your calculator, if it does not distinguish between the real and the signs of the real and the imaginary, it will give you fourth quadrant. However, this is the real is negative and the imaginary is positive. So the calculator is going to tell you minus 18.43, but that's wrong. You need to add 180 degrees to it to get it in the second quadrant. So plus 180. So the angle here would be 161.56 degrees, and V2 is 13.91 with an angle of minus 161.56 degrees. V1 is is minus 7.5, right? Divided by 5.5. Minus 7.5 divided by 5.5 of V2. So the phase angle is not going to change. Only the, of course, if you take the minus, yes. So the minus here means 180 degrees phase difference, right? So let's see how we can deal with this. V1 is 13.91 times 7.5 divided by 5.5. So it's going to be minus 18.97 minus 161.56 degrees. Now this minus 18.97 means 180 degrees phase shift. So in this case, right now I'm here with in the third quadrant, because now this one became, now I'm here, and I need to add 180 degrees phase shift if I want to write this one in positive. So in this case, the best way is to add 180 degrees in order to get the phase angle. Instead of going minus 180 degrees, we will add 180 degrees. So in this case, this V1 this minus will be translated into 180 degrees. So 18.97, right? 180 minus 161. Now we need to find Ix. So the whole objective is to find Ix, and we said that we know Ix was V1 divided by minus J 2.5. So if we keep V1 here as negative, Ix as minus 18.97 minus 161.56 degrees divided by, this is minus J. Anyway, let's keep it as 18. I'll show you why. Just leave it as 18.97, 18.4 degrees, and this is 2.5 minus J is minus 90 degrees. So Ix as 18 0.97 divided by 2.5, 7.9. Now this minus 90 degrees, when it goes up, becomes positive 90. So we have 18.44 plus 90 degrees. And the angle would be 108.44 degrees. We're not done yet. This is the phasor representation. Now we're going to go to the time domain. So in this case, Ix becomes the magnitude 7.59 cosine. How much was the was 4? Yeah. 40 plus 108.44 ampere. This is the time domain for the current Ix. Any question about how did we get the current Ix? Any question? So this is our last lecture. Starting from next week, we will be having office hours. I will post the office hours that we will be having starting from next week. We do have an office hour tomorrow as well. I encourage you to come and participate, ask whatever questions that you would like to ask and get the answers. Take advantage of this time to get a feedback from me about any question that you would like to practice yourself on your own, and then you can discuss the solution with me. Make use of the time. I am here to help you whenever you need the help. So I really encourage you to take advantage of this, of those times dedicated for you. One more thing, I really encourage you to fill up the evaluation form if you haven't done it yet. Please go ahead and submit your course evaluation. Your feedback is important to us. Would like to hear from you always. If you have any question, please ask. I need to also finalize the. I need to let you know about the way we're conducting the final exam with responders or without responders. I'll let you know. And yes, that's it. No, I would like to have it as positive. That's what I said. We always would like to have our final answer as positive cosine. So you will be taking care of the phase shift and the function itself. Remember, we talked about how to go from cosine to sine. Sorry, from positive sine to cosine, or from negative sine to cosine. So we always would like to keep it as positive cosine as our reference. Okay. Thank you so much, and I'll see you in the coming office hours on Friday. Thank you. Have a good day. Please don't hesitate to email me if you have any question. a good day.